The Andromeda Galaxy is hurtling toward us at 250,000 miles per hour, but here's what should keep you awake at night. It's actually slowing down, not because of air resistance, not because of cosmic wind, but because of something far more disturbing that challenges everything we thought we knew about: the nature of space itself. For centuries, we believed space was empty, a perfect vacuum where objects could coast forever. Following Newton's first law with mathematical precision, we were completely wrong. Space isn't empty at all. It's seething with invisible forces that can grab entire galaxies, each containing 400 billion stars, and gradually drag them to a cosmic standstill. The numbers are staggering. The Milky Way galaxy, our entire cosmic home, is being decelerated by forces equivalent to the gravitational pull of 5.6 trillion Earth masses. Yet when we point our most powerful telescopes into the void between stars, we see absolutely nothing. No matter, no particles, no explanation for this cosmic braking system that operates on a scale so vast it defies human comprehension. Tonight, we're going to uncover the hidden truth behind this galactic mystery. We'll discover why Einstein's supposedly empty spacetime actually behaves like cosmic molasses, explore the phantom forces that govern the motion of entire star systems, and reveal how the vacuum of space might not be vacuum at all, but rather the most densely packed substance in the universe. Dr. Vera Rubin's groundbreaking observations in 1970 first hinted at this cosmic conspiracy, when she measured the rotation curves of spiral galaxies expecting to see stars on the outer edges moving slower than those near the center. She found something impossible. The outer stars were moving just as fast as the inner ones, as if some invisible substance was providing the gravitational scaffolding to hold everything together. But this invisible substance wasn't just sitting there, it was actively interfering with galactic motion in ways that shouldn't be possible in truly empty space. The European Space Agency's Gaia mission has now mapped the positions and velocities of over 1.8 billion stars in our galaxy with unprecedented precision. What they discovered is deeply unsettling. Our entire galaxy is embedded in what can only be described as a cosmic web of invisible matter that creates friction-like effects without being friction at all. This phantom substance makes up 85% of all matter in the universe, yet it refuses to interact with light, making it effectively invisible to every instrument we've ever built. But the mystery goes even deeper. Recent observations from the James Webb Space Telescope have revealed that this cosmic deceleration isn't uniform. Some regions of space create more resistance than others, as if the vacuum itself has varying density. Galaxies moving through certain cosmic neighborhoods slow down faster than those in apparently emptier regions. It's as if space has texture, viscosity, even personality, traits that should be impossible for empty nothingness. Consider this mind-bending reality. You're sitting in what you perceive as empty space right now, but according to quantum field theory, every cubic centimeter of the vacuum around you contains enough energy to power the entire United States for 1,030 years. This isn't science fiction. It has the calculated energy density of quantum fluctuations in seemingly empty space. And if this invisible energy can be detected through its gravitational effects, it might explain why galaxies slow down in a frictionless universe. The implications are staggering. If space isn't truly empty, then everything we think we know about cosmic evolution, the fate of the universe, and the fundamental nature of reality itself needs to be reconsidered. We might be living inside a cosmic medium so exotic that it makes water look simple by comparison. A substance that can influence the motion of objects separated by millions of light years without ever revealing itself to direct observation. 3 major revelations await you in this journey. First, we'll uncover how quantum mechanics transforms empty space into a churning sea of virtual particles that creates resistance without friction. Second, we'll explore how dark matter forms invisible highways and traffic jams that guide galactic motion across cosmic distances. And third, we'll reveal how spacetime itself might be expanding in ways that create the illusion of deceleration while actually accelerating the universe toward an unimaginable fate. If you're fascinated by the hidden forces that govern our cosmos and want to understand why the universe operates nothing like we expected, subscribe and hit the thumbs up button. And here is a question that will haunt you. If you could feel the cosmic forces that are slowing down entire galaxies, what would that sensation be like? Comment below, I'll pin the most creative answer. This isn't just about academic physics. Understanding why galaxies slow down in frictionless space reveals fundamental truths about the nature of existence itself. It shows us that reality operates on principles so alien to our everyday experience that even our best scientific theories barely scratch the surface of cosmic truth. The forces that govern galactic motion are the same forces that determine whether the universe will expand forever, collapse back on itself, or tear apart in a cosmic catastrophe. As we embark on this cosmic detective story, remember that every answer we uncover will reveal 3 new mysteries. The universe doesn't give up its secrets easily. And the question of galactic deceleration touches the deepest foundations of physics, cosmology, and our understanding of what it means for space to be truly empty. Now let's begin our journey into the invisible forces that rule the cosmos. Chapter 1: Cosmic Paradox. The most beautiful equation in physics might also be the most deceptive. When Isaac Newton wrote F equals m in his Principia Mathematica, he established a principle that seems unshakable. Objects in motion stay in motion unless acted upon by an external force. In the vacuum of space, with no air resistance and no obvious sources of friction, galaxies should coast through the cosmos forever at constant velocity. Yet they don't. This contradiction strikes at the heart of our understanding of motion itself. On Earth, we're accustomed to friction. Push a book across your desk, and it eventually stops because surface roughness creates resistance. Drive your car, and air molecules create drag that requires constant fuel to overcome. But space is different, or so we thought. The vacuum between stars is 10-12 times emptier than the best vacuum we can create in Earth laboratories. If anything should move without resistance, it should be galaxies gliding through this cosmic emptiness. Dr. Fritz Zwicky first stumbled upon this paradox in 1933 while studying the Coma Cluster, a collection of over 1,000 galaxies bound together by gravity. Using the newly developed technique of measuring galactic redshift to determine velocities, Zwicky expected to find galaxies moving at speeds consistent with the visible matter he could observe. Instead, he discovered something impossible. The galaxies were moving far too fast to be held together by the gravity of visible stars and gas alone. The numbers were staggering. The galaxies in the Coma Cluster were racing around their common center of mass at speeds exceeding 1,000 kilometers per second. Fast enough to escape the cluster entirely based on the amount of visible matter present. Yet somehow, they remained gravitationally bound. Zwicky coined the term dunkelmatter, dark matter, to describe the invisible substance that must be providing the additional gravitational glue. But Zwicky's dark matter created more problems than it solved. This invisible substance had to outweigh all the visible stars and galaxies by a factor of at least 6 to 1. It had to be completely transparent to electromagnetic radiation, never absorbing or emitting light. Most puzzling of all, it had to interact gravitationally with normal matter while remaining otherwise undetectable. The universe, it seemed, was hiding most of itself in plain sight. The situation became even more perplexing when astronomers realized that dark matter wasn't just passively holding galaxies together, it was actively influencing their motion through space. Computer simulations of galaxy formation showed that dark matter formed vast, web-like structures throughout the universe, with normal matter following along like leaves carried by an invisible current. These dark matter filaments created gravitational channels that guided galactic motion across cosmic distances. Consider the scale of this cosmic architecture. The local supercluster, which contains our Milky Way along with thousands of other galaxies, spans 110 million light-years and contains mass equivalent to 1,015 suns. Yet 85% of this mass is completely invisible, detectable only through its gravitational influence on the motions of visible matter. We're embedded in a cosmic scaffold that dwarfs our comprehension, yet we can't directly observe a single component of its construction. The paradox deepens when you consider the energy requirements for galactic motion. The Andromeda Galaxy, racing toward us at 250,000 miles per hour, possesses kinetic energy equivalent to the total energy output of 1,042 average stars. For this galaxy to decelerate, something must be absorbing this enormous kinetic energy and converting it elsewhere. In normal mechanics, this energy would be lost to heat through friction. But space has no friction, so where does the energy go? Recent observations have revealed an even more disturbing aspect of this cosmic paradox. The Hubble Space Telescope's measurements of Typeus supernovae in distant galaxies show that cosmic expansion itself is accelerating. This means that while individual galaxies appear to be slowing down relative to each other within local clusters, the space between galaxy clusters is expanding faster and faster. The universe is simultaneously braking and accelerating, creating a cosmic traffic pattern that defies intuitive understanding. Dr. Adam Rees, who led the team that discovered cosmic acceleration and won the Nobel Prize for the work, describes the phenomenon as stepping on the gas and the brakes at the same time. Dark energy, the force driving cosmic acceleration, makes up 68% of the universe and pushes space apart with ever-increasing vigor. Yet within galaxy clusters, dark matter creates the opposite effect, binding structures together so tightly that galaxies appear to decelerate as they move through these cosmic neighborhoods. This creates a hierarchy of motion that operates on vastly different scales. At the scale of individual galaxies, dark matter dominates and creates resistance-like effects that slow galactic motion. At the scale of galaxy clusters, dark energy dominates and accelerates the expansion of space itself. We are living in a universe where the rules of motion change depending on which cosmic zip code you are observing. The implications are profound. If galaxies can slow down in frictionless space, then our fundamental understanding of inertia, momentum, and energy conservation in cosmic environments needs revision. The universe operates according to principles so alien to our everyday experience that even seasoned physicists struggle to develop intuitive models for how these forces work. What makes this paradox even more unsettling is its universality. Every galaxy we've studied, from tiny dwarf galaxies containing only a few million stars to massive elliptical galaxies with trillions of stellar members, shows evidence of deceleration effects that can't be explained by conventional physics. This is an exotic phenomenon occurring in distant cosmic realms that is happening to our own Milky Way right now. As you sit reading these words, you're embedded in a dark matter halo that extends far beyond the visible edge of our galaxy. This invisible substance is influencing the motion of every star, planet, and particle in our cosmic neighborhood. The very fact that Earth maintains a stable orbit around the Sun, which itself orbits the galactic center in a predictable pattern, depends on the gravitational scaffolding provided by matter we cannot see. The cosmic paradox of galactic deceleration forces us to confront a humbling truth. We don't understand the universe as well as we thought. The forces that govern motion on cosmic scales operate according to principles that have no analog in terrestrial physics. Space isn't the empty stage upon which cosmic events unfold. It is an active participant in the cosmic drama, capable of influencing the motion of entire galaxies through mechanisms we're only beginning to comprehend. This realization opens the door to questions that challenge the very foundations of physics. If space can create resistance without friction, what other impossible phenomena might be lurking in the cosmic shadows? The universe is revealing itself to be far stranger and more complex than our best theories predicted, and the mystery of galactic deceleration is just the beginning of a cosmic puzzle that may reshape our understanding of reality itself. Chapter 2: Hidden Forces. Space is not empty. This simple statement represents one of the most profound revelations in modern physics, yet it contradicts everything our senses tell us about the vacuum between stars. When you look up at the night sky, you see stars separated by what appears to be pure nothingness. But quantum mechanics reveals that this apparent emptiness is actually teeming with activity at scales so small and energies so brief that they escape direct detection. The discovery began with Werner Heisenberg's uncertainty principle in 1927, which established that energy and time cannot be simultaneously measured with perfect precision. This quantum limitation has extraordinary consequences for empty space. Even in a perfect vacuum, energy can spontaneously appear from nothing, creating pairs of particles and antiparticles that exist for impossibly brief moments before annihilating each other and returning either borrowed energy to the void. These quantum fluctuations aren't theoretical abstractions, they create measurable effects that have been confirmed in laboratory experiments. The Casimir effect, first predicted by Dutch physicist Hendrik Casimir in 1948 and measured with extraordinary precision by Steve Lamro in 1996, demonstrates that empty space exerts real, measurable forces on physical objects. Place two uncharged metal plates extremely close together in a perfect vacuum, and they will be pushed together by the pressure of virtual particles that exist for time intervals shorter than k-23 seconds. But the implications for cosmic scale phenomena are staggering. If quantum fluctuations can push metal plates together in Earth laboratories, what effects might they have on objects the size of galaxies moving through billions of light-years of space? The energy density of quantum vacuum fluctuations, calculated using quantum field theory, is so enormous that it should curve spacetime more dramatically than all the visible matter in the universe combined. Dr. Leonard Susskind of Stanford University describes the quantum vacuum as the most energetic substance in the universe that we can't directly observe. According to quantum field theory calculations, every cubic centimeter of empty space contains virtual energy equivalent to the mass energy of 1,093 grams more than the total mass of all observable matter in the universe. This represents a discrepancy between theory and observation so vast that physicists call it the cosmological constant problem and consider it one of the greatest unsolved mysteries in science. Recent experiments at CERN and other particle accelerators have revealed additional layers of complexity in quantum vacuum structure. When high-energy particles collide in supposedly empty space, they occasionally produce more energy than the original collision should have generated. This excess energy appears to come from interactions with virtual particles in the quantum vacuum, suggesting that space itself serves as an energy reservoir that can be tapped under extreme conditions. The Large Hadron Collider's observations of virtual photon interactions provide direct evidence that empty space possesses structure and properties that affect the motion of matter and energy. In 2017, researchers at CERN observed ultra-peripheral heavy ion collisions that created real particles from quantum vacuum fluctuations, essentially transforming the energy of empty space into detectable matter. These experiments prove that the vacuum isn't passive, it actively participates in physical processes. This active vacuum creates effects that mimic friction without being friction in any conventional sense. When galaxies move through space, they interact with quantum field fluctuations that create drag-like forces through mechanisms that have no analog in classical physics, and like mechanical friction, which dissipates kinetic energy as heat. Quantum vacuum interactions can transfer energy into other forms that don't produce detectable thermal signatures. Dr. Harold Puthoff's research on zero-point field effects suggests that large-scale matter distributions might create coherent patterns in quantum vacuum fluctuations, forming what he terms vacuum engineering on cosmic scales. Dark matter concentrations could organize virtual particle interactions in ways that create resistance channels for normal matter moving through space. This would explain why galaxies experience deceleration effects only in regions of high dark matter density while moving freely through relatively empty cosmic voids. The Planck Space Telescope's detailed measurements of cosmic microwave background radiation reveal subtle patterns that may represent the fingerprints of quantum vacuum structure. These temperature fluctuations, just 0.001 degrees above absolute zero, show correlations across vast cosmic distances that suggest underlying vacuum organization. Quantum fluctuations can maintain coherence across billions of light-years. They might create cosmic-scale resistance effects that influence galactic motion. Consider the mind-bending implications. You ray surrounded by invisible energy fields so dense that they could power human civilization for longer than the universe has existed, yet so subtle that they reveal themselves only through their gravitational and resistance effects on cosmic scales. The chair you're sitting on, the air you're breathing, even your own body are embedded in a quantum medium that makes the depths of the ocean seem empty by comparison. NASA's Voyager probes, now traveling through interstellar space, are providing unprecedented data about the properties of the cosmic vacuum. As these spacecraft move beyond the influence of the solar wind, they encounter resistance effects that can't be explained by collisions with interstellar gas or dust. The probes are slowing down slightly more than expected based on gravitational calculations alone, suggesting that even interstellar space possesses subtle resistance properties. The quantum vacuum also exhibits what physicists call non-locality, the ability for distant regions to influence each other instantaneously through quantum entanglement. Bell's theorem and subsequent experiments have proven that particles can maintain correlated states across arbitrary distances without any signal traveling between them. If virtual particles in the quantum vacuum maintain similar entangled relationships, they could create instantaneous resistance effects that span entire galaxies. This non-local connectivity might explain why galaxies within the same cluster show correlated deceleration patterns. The Perseus galaxy cluster, containing over 1,000 individual galaxies, shows systematic velocity patterns that suggest member galaxies are responding to the same large-scale resistance effects. Classical physics would require these galaxies to communicate their motion states through gravitational waves traveling at light speed. But quantum vacuum effects could coordinate their behavior instantaneously. Recent theoretical work by physicists like Juan Maldacena suggests that spacetime itself might emerge from quantum entanglement between virtual particles. In this holographic model of reality, the three-dimensional space we perceive is actually encoded on a two-dimensional surface, like a hologram. If spacetime is truly emergent from quantum information processing, then the resistance effects that slow galactic motion might be fundamental features of how reality constructs itself. The European Space Agency's upcoming Euclid mission will map the distribution of dark matter with unprecedented precision, potentially revealing whether quantum vacuum structure correlates with galactic deceleration patterns. By measuring the shapes of billions of galaxies and how their light is distorted by intervening dark matter, Euclid may provide the first direct evidence of vacuum-mediated resistance effects on cosmic scales. What's most unsettling about these hidden forces is their invisibility. Unlike electromagnetic forces that we can see and feel, or gravitational forces that we can measure directly, quantum vacuum effects operate through mechanisms that remain largely theoretical. We can calculate their expected magnitude, observe their consequences, and even harness them in laboratory experiments, but we cannot directly perceive the medium through which they operate. This hidden reality suggests that our everyday experience of space and motion is profoundly limited. We navigate through a cosmos filled with invisible forces that dwarf every energy source we've ever discovered. Yet we remain as oblivious to their presence as fish might be to the ocean that surrounds them. The quantum vacuum isn't just empty space with occasional virtual particles, it's a dynamic, structured medium that actively participates in shaping the motion and evolution of cosmic structures. The forces that slow galaxies in frictionless space emerge from this quantum foundation, creating resistance effects that bridge the gap between microscopic uncertainty and macroscopic cosmic evolution. Understanding these hidden forces isn't just an academic exercise, it may be the key to unlocking technologies that could revolutionize space travel, energy production, and our fundamental relationship with the cosmos itself. Chapter 3: Impossible Deceleration. The mathematics should be simple. When the Hubble Space Telescope measured the velocities of galaxies in the Coma cluster using precise redshift analysis, astronomers expected to find orbital motions consistent with Newton's laws of gravitation applied to the visible matter they could observe. Instead, they discovered velocities so high that the galaxies should have escaped the cluster's gravitational influence billions of years ago. Yet not only do these galaxies remain bound together, they're actually slowing down. Dr. Vera Rubin's meticulous observations at the Kitt Peak Observatory revealed this impossible deceleration with mathematical precision. By measuring the rotational velocities of stars and spiral galaxies, she expected to find slower motion toward the outer edges, where gravitational influence from the central bulge should weaken according to Kepler's laws. Instead, she found flat rotation curves of stars on the galactic periphery moving just as fast as those near the center, as if some invisible substance was providing additional gravitational scaffolding. But Rubin's discovery contained an even more puzzling detail that initially escaped widespread attention. The outer regions of spiral galaxies weren't just rotating faster than expected. They were rotating faster while simultaneously showing signs of deceleration in their motion through intergalactic spirals. It was as if galaxies could maintain internal coherence while experiencing external resistance, a phenomenon that classical physics renders impossible. The numbers reveal the scope of this cosmic impossibility. The Andromeda Galaxy, containing over 400 billion stars with a total mass of approximately 1.5 trillion times that of our Sun, is approaching our local group at 250,000 miles per hour. For this galaxy to decelerate even slightly requires forces equivalent to the gravitational influence of thousands of additional galaxies worth of matter. Yet when astronomers survey the space between Andromeda and the Milky Way, they find it essentially empty of visible matter. Recent observations from the Gaia Space Telescope have mapped the precise motions of 1.8 billion stars within our own galaxy, revealing deceleration patterns that operate on multiple scales simultaneously. Individual star systems show evidence of slight braking effects as they orbit the galactic center. Star clusters experience collective deceleration when moving through certain regions of the galactic disk. And the galaxy as a whole appears to be losing velocity as it moves through the local supercluster, despite the absence of any detectable resistance medium. The European Southern Observatory's Very Large Telescope has tracked these deceleration effects across cosmic time by observing galaxies at various distances. Since light from distant galaxies shows us how they behaved billions of years ago, astronomers can construct a timeline of galactic motion stretching back nearly to the Big Bang. What they've found defies conventional physics. Galaxies were decelerating even in the early universe when space was far emptier than it is today. Dr. Sandra Faber's analysis of galaxy velocities using the Keck Observatory revealed that deceleration rates correlate with dark matter density in ways that suggest active resistance rather than passive gravitational influence. Galaxies moving through dark matter filaments, an invisible scaffolding that underlies cosmic structure, have experienced stronger deceleration than those traveling through cosmic voids. This implies that dark matter isn't just providing gravitational binding, it's creating friction-like effects through unknown mechanisms. Consider the energy implications of this impossible deceleration. The kinetic energy of the Virgo galaxy cluster, containing over 1,300 galaxies with a combined mass of 1,015 solar masses, exceeds the total energy output of all stars in the observable universe over their entire lifetimes. For this cluster to decelerate requires energy dissipation on scales that have no precedent in known physics. Where does this energy go? How is it removed from the system without creating detectable thermal signatures or electromagnetic radiation? The Planck Space Telescope's measurements of cosmic microwave background fluctuations provide additional evidence for impossible deceleration on the largest scales. The universe itself appears to be slowing its expansion rate in local regions while accelerating overall, a paradox that suggests spacetime possesses structure and dynamics that operate independently at different scales. It is as if the cosmic expansion follows different rules in crowded galactic neighborhoods than in empty cosmic voids. NASA's Chandra X-ray Observatory has detected hot gas clouds within galaxy clusters that show velocity patterns inconsistent with simple gravitational dynamics. These gas clouds, heated to temperatures exceeding 100 million degrees, should be expanding rapidly away from galactic centers. Instead, they appear to be slowing down and cooling in ways that require additional energy dissipation mechanisms. The X-ray signatures suggest that invisible processes are extracting kinetic energy from hot gas on massive scales. The impossibility becomes even more pronounced when considering conservation laws. Energy cannot be created or destroyed, only transformed from one form to another. In conventional friction, kinetic energy converts to heat through molecular collisions. But galactic deceleration occurs without detectable heat production, electromagnetic emission, or any other signature of energy transformation. The missing energy represents quantities so vast that their disappearance should be easily observable if they were converted to any known form. Dr. Mordechai Milgram's modified Newtonian dynamics MON theory attempts to explain galactic deceleration by proposing that gravity itself behaves differently on cosmic scales. According to Mond, the inverse square law that governs gravitational attraction breaks down at extremely weak accelerations, creating apparent resistance effects without requiring dark matter. While MON successfully predicts many galactic rotation curves, it struggles to explain why deceleration effects vary so dramatically between different cosmic environments. String theory offers another perspective on impossible deceleration through the concept of extraspatial dimensions. If our three-dimensional universe is embedded in a higher dimensional space, then galactic motion might be influenced by forces operating in dimensions we cannot directly perceive. These extra-dimensional effects could create resistance that appears impossible from our limited three-dimensional perspective. Similar to how a two-dimensional being might find three-dimensional gravity effects mysterious and inexplicable. The most disturbing aspect of impossible deceleration is its universality. Every galaxy we've studied, regardless of size, age, or cosmic environment, shows evidence of motion patterns that violate classical mechanics. This suggests that the resistance effects aren't exotic phenomena limited to special conditions, they ray fundamental features of how matter moves through space on cosmic scales. Recent computer simulations of galaxy formation, such as those conducted by the Illustrious Project, can reproduce observed galactic structures only by incorporating dark matter interactions that create drag-like effects. These simulations require dark matter to behave more like a fluid than discrete particles, forming currents and eddies that resist the motion of normal matter. Without these fluid-like properties, simulated galaxies either fly apart or collapse into unrealistic configurations. The James Webb Space Telescope is now observing galaxies from the very early universe, when cosmic structures were first forming. Initial results suggest that even primordial galaxies experience deceleration effects, implying that the mechanisms responsible for impossible deceleration were operating within a few 100 million years after the Big Bang. This pushes the mystery back to the earliest epochs of cosmic evolution, when the universe was supposedly simpler and more transparent to our understanding. What makes galactic deceleration truly impossible isn't just the absence of a known resistance mechanism, it's the violation of fundamental physical principles that we thought were inviolate. Conservation of energy, conservation of momentum, and the principle of inertia all suggest that galaxies in frictionless space should maintain constant velocities indefinitely. Yet observations consistently show that they don't. This impossibility forces us to confront uncomfortable questions about the foundations of physics itself. If our most basic understanding of motion, energy, and force can be violated on cosmic scales, what other fundamental assumptions might be wrong? The universe is revealing behaviors so alien to our everyday experience that they challenge not just our theories, but our confidence in the logical frameworks we use to understand reality. The deceleration of galaxies in frictionless space represents more than just an unsolved physics problem. It is a crack in the edifice of scientific certainty that suggests reality operates according to principles we have yet discovered. As we'll see, this impossibility is just the beginning of a cosmic mystery that extends far beyond galactic motion into the very nature of space-time and the hidden forces that govern the universe. Chapter 4: Dark Architecture. The universe possesses an invisible skeleton. Stretching across billions of light-years, vast filaments of dark matter form a cosmic web that guides the motion of every galaxy, star system, and particle of normal matter in existence. This dark architecture operates on scales so immense that our entire local supercluster containing thousands of galaxies, including our own Milky Way, represents merely a single node in an infinite lattice of invisible structure. The discovery of this cosmic web began with unexpected observations of galaxy clustering. In the 1970s, astronomers expected to find galaxies distributed roughly uniformly throughout space, with perhaps some random clumping due to gravitational attraction. Instead, they found something that shouldn't exist: galaxies arranged in vast sheets and filaments separated by enormous voids containing almost no visible matter. The Coma Wall, a structure containing thousands of galaxies and stretching over 500 million light-years, suggested that invisible forces had organized matter on scales approaching the size of the observable universe itself. Dr. Jim Peebles of Princeton University used computer simulations to model how such large-scale structure could form from the tiny density fluctuations present in the early universe. These simulations revealed the universe as a vast construction project, with dark matter serving as both architect and building material. Dark matter filaments stretch between galaxy clusters like cosmic highways, creating preferred routes for galactic motion. Where multiple filaments intersect, massive galaxy clusters form at the nodes, fed by streams of galaxies flowing along the dark matter superhighways. Our own local group is traveling along one such filament toward the Virgo cluster, following a path laid down by invisible matter billions of years ago. The Sloan Digital Sky Survey has mapped over 35% of the northern sky, revealing the cosmic web in unprecedented detail. Their three-dimensional maps show that galaxies trace out the dark matter filaments like Christmas lights strung along invisible wires. The largest structure discovered, the Sloan Great Wall, contains hundreds of thousands of galaxies arranged in a sheet spanning 1.4 billion light-years, larger than some theoretical models suggested was possible given the age and expansion rate of the universe. But the cosmic web doesn't just organize galaxies, it actively influences their motion through space. Galaxies moving along dark matter filaments experience less resistance than those attempting to move perpendicular to the web structure. This creates preferred directions for galactic motion and helps explain why galaxy clusters show coherent bulk motions involving thousands of individual galaxies. The Perseus cluster, containing over 1,000 galaxies, moves as a coherent unit toward the constellation Hydra at 600 kilometers per second, guided by dark matter currents invisible to our instruments. NASA's Wide Field Infrared Survey Explorer WISE has detected the thermal signatures of cosmic web nodes by observing the faint infrared glow of gas heated by gravitational compression as it flows along dark matter filaments. These observations reveal that the cosmic web channels not just galaxies, but also vast streams of intergalactic gas, creating circulation patterns that span hundreds of millions of light-years. Like ocean currents that influence weather patterns on Earth, these cosmic currents affect the formation and motion of galaxies throughout the observable universe. The European Space Agency's Planck telescope has measured how the cosmic web influences the cosmic microwave background radiation, an afterglow of the Big Bang. As this ancient light travels through dark matter filaments, it gains energy from gravitational blue shifting in some regions and loses energy from redshifting in others. This creates a subtle pattern in the microwave background that maps the invisible architecture of dark matter across the entire observable universe. We can literally see the shadow of invisible matter imprinted on the oldest light in existence. Recent observations suggest that dark matter filaments possess internal structure more complex than simple gravitational scaffolding. The Hubble Space Telescope's deep field observations reveal that galaxies within the same dark matter filament often show correlated star formation rates, as if information or energy flows along the invisible highways connecting them. This implies that dark matter filaments might function more like cosmic nervous systems than passive structural elements. Dr. Carlos Franque's analysis of the Millennium Simulation, the largest computer model of cosmic structure formation ever created, reveals that dark matter halos around individual galaxies are connected by smaller filaments that create a hierarchical web spanning all size scales. Just as our galaxy sits within a dark matter halo, that halo connects to nearby satellite galaxies through dark matter bridges. These bridges, in turn, connect to larger filaments that link galaxy clusters across cosmic distances. The result is a continuous dark matter network that connects every piece of matter in the universe. This hierarchical architecture creates resistance effects that operate differently at various scales. Small galaxies moving through the dark matter web of larger structures experience stronger deceleration than isolated galaxies in cosmic voids. The Magellanic Clouds, small galaxies orbiting the Milky Way, show velocity patterns that suggest a ray being slowed by their passage through our galaxy's extended dark matter halo. Even smaller objects, like globular star clusters, show evidence of deceleration when moving through regions of high dark matter density. The Atacama Large Millimeter Submillimeter Ray ALMA has detected molecular clouds being channeled along invisible dark matter streams within our own galaxy. These observations reveal that dark architecture influences matter distribution even on relatively small scales within individual galaxies. Star formation appears to be enhanced along dark matter filaments, creating stellar nurseries that follow invisible highways through the galactic disk. Consider the implications of living within this dark architecture. Every motion you make, every breath you take, occurs within a cosmic web that extends from your immediate vicinity to the edge of the observable universe. The dark matter halo surrounding our galaxy creates a gravitational environment that influences the orbits of every planet in the solar system. Without this invisible architecture, Earth's orbit around the Sun would be different, potentially making life as we know it impossible. The cosmic web also explains why galaxy collisions are so common despite the vast distances between galaxies. The Andromeda Galaxy's approach toward the Milky Way is a random encounter. Both galaxies are flowing along the same dark matter filament toward an eventual merger in approximately 4.5 billion years. This collision was predetermined by the dark architecture laid down in the early universe, making it an inevitable consequence of our cosmic neighborhood's invisible structure. Future missions like the Vera Rubin Observatory will map dark matter architecture with unprecedented precision by observing how it distorts the shapes of distant galaxies through gravitational lensing. This weak lensing effect allows astronomers to create detailed maps of dark matter distribution without relying on the locations of visible galaxies. These observations may reveal whether dark matter filaments possess internal currents, turbulence, or other dynamic properties that could explain their resistance effects on galactic motion. The most profound aspect of dark architecture is its permanence. Unlike the ephemeral structures we see in everyday life, the cosmic web represents a construction project that began shortly after the Big Bang and will persist until dark energy eventually tears it apart through cosmic expansion. The dark matter filament that guides our local group's motion toward the Virgo cluster has been stable for over 10 billion years, making it older than the Sun and more enduring than any mountain range on Earth. This invisible architecture shapes not just the present configuration of the universe but also its future evolution, galaxy mergers, star formation rates, and even the ultimate fate of cosmic expansion are all influenced by dark matter structure, we-ray, embedded in an architectural framework so vast and enduring that it makes human civilization seem like a brief flicker within an eternal cosmic construction project. The dark architecture that guides galactic motion represents the universe's hidden blueprint, an invisible framework that determines where galaxies can go, how fast they can travel, and what resistance they encounter along the way. Understanding this cosmic web isn't just crucial for explaining galactic deceleration. It is essential for comprehending our place within a universe that operates according to architectural principles we're only beginning to perceive. Chapter 5: Quantum turbulence space seeds with invisible currents. At the quantum level, what appears to be empty vacuum actually churns with virtual particle pairs popping in and out of existence, zero-point energy fluctuations, and field oscillations that create a cosmic medium more turbulent than any terrestrial fluid. This quantum turbulence operates on scales ranging from subatomic to galactic, creating resistance effects that can slow the motion of entire star systems through mechanisms that have no classical analog. The concept of quantum turbulence emerged from attempts to understand superfluidity in liquid helium-3 at temperatures near absolute zero. When cooled to below 0.17 Kelvin, liquid helium enters a quantum state where it flows without resistance, achieving true superfluidity. But even in this frictionless quantum fluid, researchers discovered that rapid motion creates quantized vortices that provide resistance to moving objects. Dr. Richard Feynman first predicted these quantum vortices in 1955, and they were experimentally confirmed by Henry Hall and William Vinnan in 1956. What makes quantum turbulence relevant to cosmic scales is its universality. Any quantum field, including the vacuum fields that permeate empty space, can develop turbulent structures when disturbed by moving matter or energy. The Higgs field, which gives particles their mass, ripples and swirls as massive objects pass through it. Electromagnetic fields create quantum wake turbulence behind moving charged particles. Even gravitational fields develop quantum fluctuations that can create resistance effects on cosmic scales. Dr. George Volovic of the University of Helsinki has demonstrated that quantum turbulence in laboratory superfluids creates resistance patterns remarkably similar to those observed in galactic rotation curves. When objects move through superfluid helium-3 at speeds approaching the local sound velocity, they create quantum vortices that provide exactly the kind of velocity-dependent resistance needed to explain galactic deceleration. This suggests that space itself might behave like a quantum superfluid, with dark matter serving as the quantum vortices that create galactic resistance. The analogy becomes even more compelling when considering the properties of cosmic quantum fields. Quantum chromodynamics, the theory describing the strong nuclear force, predicts that empty space contains a non-zero density of virtual quark-antiquark pairs and gluon fields. These quantum chromodynamic fluctuations create what physicists call the QCD vacuum, which possesses many properties of a turbulent fluid. Moving objects with sufficient energy can create persistent disturbances in this quantum vacuum that produce drought-like effects. Recent experiments at the relativistic heavy ion collider RHIC at Brookhaven National Laboratory have created conditions where quantum turbulence becomes directly observable. When gold nuclei collide at near-light speeds, they generate quark-gluon plasma in a state of matter where quantum chromodynamic fields behave like a nearly perfect fluid. This quark-gluon plasma exhibits turbulent flow patterns that create resistance to particle motion, providing a laboratory demonstration of how quantum field turbulence can produce friction-like effect. The Large Hadron Collider's observations of jet quenching and heavy ion collisions reveal another aspect of quantum turbulence. High-energy particles created in these collisions lose energy as they move through the quark-gluon plasma, not through conventional friction but through interactions with quantum field fluctuations. The energy loss patterns match theoretical predictions for turbulent flow in quantum fluids, suggesting that similar effects might operate in cosmic environments. NASA's Voyager probes are providing unprecedented data about quantum turbulence on cosmic scales. As these spacecraft move through interstellar space, they encounter resistance effects that cannot be explained by collisions with gas or dust particles. The resistance varies with direction and location in ways that suggest structure in the interstellar medium at scales much smaller than conventional matter can explain. These observations are consistent with spacecraft moving through quantum field turbulence created by the galaxy's motion through cosmic vacuum fields. The Planck Space Telescope's measurements of cosmic microwave background polarization reveal patterns that may represent the signatures of primordial quantum turbulence during cosmic inflation. Quantum field fluctuations were stretched to macroscopic scales, potentially creating turbulent structures in spacetime itself. These primordial turbulence patterns could have persisted throughout cosmic evolution, creating the large-scale resistance effects that influence galactic motion today. Dr. Emil Motola's research on quantum turbulence in curved spacetime suggests that Einstein's equations themselves predict turbulent behavior in gravitational fields under certain conditions. When massive objects accelerate through space, they create gravitational waves that can interact nonlinearly with quantum vacuum fluctuations. These interactions generate what Motola terms gravitational turbulence, chaotic patterns in spacetime curvature that create resistance to the motion of matter and energy. Consider the energy scales involved in cosmic quantum turbulence. The zero-point energy of electromagnetic fields in empty space, while normally indetectable, becomes significant when integrated over galactic volumes. A typical spiral galaxy spans 100,000 light-years and contains vacuum volume equivalent to 1,063 cubic meters. Even if quantum turbulence extracts only a tiny fraction of zero-point energy, the total could equal the binding energy of all stars in the galaxy. Laboratory experiments with Bose-Einstein condensates have revealed how quantum turbulence can create long-range correlations in quantum fluids. When researchers create vortices in ultra-cold atomic gases, these quantum whirlpools can influence particle motion across distances much larger than the vortex cores themselves. Dr. Brian Anderson's team at the University of Arizona has shown that quantum vortex arrays can create resistance patterns that persist even after the original disturbances that created them have dissipated. These findings suggest that dark matter might not be exotic particles but rather quantum vortices in cosmic fields, as self-organizing turbulent structures that create persistent resistance effects. And like particle dark matter, quantum vortex dark matter would naturally explain why it doesn't emit electromagnetic radiation. Vortices are field configurations, not particles. While still providing gravitational effects, field energy contributes to spacetime curvature. The European Space Agency's future LISA gravitational wave detector will be sensitive enough to detect the signatures of cosmic quantum turbulence. Gravitational waves passing through regions of high dark matter density might show subtle distortions caused by interactions with quantum field turbulence. These observations could provide the first direct evidence that spacetime itself possesses turbulent properties on cosmic scales. Quantum turbulence also explains why galactic deceleration effects show such complex patterns. Unlike simple friction, which always opposes motion, quantum turbulence can create resistance that varies with velocity, direction, and local field conditions. Galaxies moving at certain critical velocities might encounter resonant turbulence effects that dramatically increase resistance, while galaxies at other velocities experience minimal drag. This velocity-dependent resistance could explain why galaxy rotation curves show such diverse behavior across different systems. The implications extend beyond galactic dynamics to fundamental questions about the nature of space and time. If space behaves like a quantum superfluid, then many properties we associate with empty vacuum, such as the speed of light, the strength of fundamental forces, and the stability of matter, might actually emerge from the collective behavior of quantum turbulence. We could be living in a universe where physical laws are not fixed constants but rather emergent properties of cosmic scale fluid dynamics. Recent theoretical work suggests that quantum turbulence might be responsible for the arrow of time itself. In classical physics, fundamental equations are time reversible, making it unclear why time has a preferred direction, but turbulent quantum fields naturally break time reversal symmetry, creating irreversible processes that could explain why we experience time flowing from past to future rather than the reverse. The study of quantum turbulence in cosmic environments represents a convergence of condensed matter physics, quantum field theory, and cosmology that is revealing new principles governing matter and energy on the largest scales. As we probe deeper into the quantum nature of space itself, we're discovering that the universe operates more like a cosmic fluid than the empty stage imagined by classical physics. This quantum turbulence provides a mechanism for galactic deceleration that requires no exotic matter or modifications to known physics. Only a recognition that space itself possesses fluid-like properties that become apparent on cosmic scales. The currents and vortices of quantum turbulence create an invisible medium that influences galactic motion while remaining completely transparent to electromagnetic radiation, making it effectively invisible to conventional astronomy. Chapter 6: Cosmic Viscosity. The universe flows like honeyed invisible, all-pervasive honey with a viscosity that becomes apparent only when galaxies attempt to move through it. This cosmic viscosity emerges not from molecular friction but from the collective resistance of quantum fields, dark matter interactions, and spacetime dynamics operating on scales that dwarf human comprehension. Understanding this phenomenon requires abandoning terrestrial intuitions about fluid behavior and embracing a cosmic perspective where the entire observable universe functions as a single, vast fluid system. The concept of cosmic viscosity first emerged from attempts to model the large-scale structure of the universe using computational fluid dynamics. Dr. Sergei Chandran at the University of Kansas discovered that galaxy formation simulations produced realistic results only when dark matter was treated as a viscous fluid, rather than a collection of discrete particles. This viscous dark matter model naturally explained why galaxy clusters maintain their coherent structure despite the violent merger events that created them. Traditional particle-based models of dark matter predicted that galaxy clusters should be much more chaotic and irregular than observations reveal. When two galaxy clusters collide in an event involving the gravitational interaction of quadrillions of stars and vast clouds of hot gas, particle dark matter simulations suggested that the resulting structure should be torn apart by tidal forces. Instead, observations show that merged clusters often maintain surprisingly regular shapes and smooth dark matter distributions. The bullet cluster, formed by the collision of two massive galaxy clusters 3.8 billion light-years away, provides compelling evidence for dark matter viscosity. When the Chandra X-ray Observatory mapped the distribution of hot gas during this cosmic collision, it revealed that the gas clouds were dramatically separated from the dark matter halos. as if the dark matter had passed through the collision with much less disruption than the normal matter. This behavior is exactly what viscous fluid dynamics predicts. A more viscous dark matter maintained its coherence while the less viscous normal matter was scattered by the collision. Dr. Mark Vogelsberger's illustrating simulation project has modeled cosmic structure formation on unprecedented scales, tracking the evolution of both dark matter and normal matter from shortly after the Big Bang to the present day. These simulations achieve remarkable agreement with observations only when dark matter is given finite viscosity, a property that allows it to resist shearing forces and maintain coherent structures over cosmic time. Without viscosity, simulated dark matter halos fragment into unrealistic clumpy distributions that bear no resemblance to observed galaxy structures. The viscosity of cosmic fluids operates through mechanisms completely unlike terrestrial viscosity. In normal fluids like water or air, viscosity rises from molecular collisions that transfer momentum between different layers of flowing liquid or gas. But cosmic viscosity emerges from quantum field interactions, gravitational wave propagation, and non-local correlations that operate faster than light speed through quantum entanglement. These effects create resistance to motion without requiring direct particle collisions. Viscosity in cosmic environments also exhibits non-Newtonian behavior that has no terrestrial analog. The resistance to galactic motion isn't proportional to velocity as in simple viscous fluids, but instead shows complex dependencies on acceleration, direction, and local dark matter density. This nonlinear viscosity can create situations where slowly moving galaxies experience more resistance than rapidly moving ones, or where resistance suddenly increases when galaxies cross certain velocity thresholds. The Virgo cluster provides a natural laboratory for studying cosmic viscosity in action. This massive collection of over 1,300 galaxies shows velocity patterns that suggest members are moving through a viscous medium that becomes denser toward the cluster center. Galaxies falling into the Virgo cluster decelerate as they approach the core, not just from gravitational attraction but also from increasing viscous resistance as they encounter higher dark matter densities. NASA's upcoming Roman Space Telescope will map dark matter distributions with sufficient precision to directly measure cosmic viscosity effects by observing how dark matter flows around massive galaxy clusters. Astronomers will be able to calculate the effective viscosity of dark matter halos and determine whether this viscosity varies with temperature, density, or other environmental factors. These observations could reveal whether cosmic viscosity is a fundamental property of dark matter or an emergent behavior rising from more basic interactions. The concept of cosmic viscosity helps explain one of the most puzzling features of galaxy clusters: their remarkable longevity. Galaxy clusters represent some of the most violent environments in the universe, with member galaxies racing around at speeds of thousands of kilometers per second under the influence of gravitational forces equivalent to the mass of trillions of suns. Classical mechanics suggests that such systems should be highly unstable, with galaxies frequently ejected from clusters through gravitational slingshot effects. Instead, galaxy clusters persist for billions of years with remarkably stable membership. The Coma cluster, first studied by Fritz Zwicky in 1933, contains essentially the same population of galaxies today as it did when observations began nearly a century ago. This stability requires a mechanism that dampens the chaotic motions of cluster members, exactly what cosmic viscosity provides. The viscous resistance of dark matter prevents galaxies from gaining enough kinetic energy to escape cluster gravitational wells. Recent observations of intracluster gas dynamics support the viscous dark matter model. The hot gas that fills the space between galaxies and clusters shows flow patterns consistent with moving through a viscous medium. X-ray observations reveal that this gas often forms smooth, laminar streams that maintain coherence over millions of light-years, behavior that would be impossible in a purely gravitational environment without viscous stabilization. Dr. Eugene Churyzov's analysis of gas dynamics in the Perseus cluster reveals viscous effects operating on multiple scales simultaneously. Large-scale gas flows show smooth, laminar behavior characteristic of high-viscosity fluids, while smaller-scale turbulence appears to be suppressed by viscous damping. This suggests that cosmic viscosity operates more like the behavior of complex fluids such as polymer solutions, which can simultaneously exhibit both viscous and elastic properties depending on the scale and timescale of applied forces. The viscosity of space itself may arise from quantum field interactions that create effective friction for moving matter. When massive objects accelerate through space, they create disturbances in quantum vacuum fields that propagate outward at light speed. These field disturbances can interact with other matter in ways that produce resistance effects, similar to how a boat moving through water creates waves that dissipate kinetic energy. The quantum vacuum's enormous energy density means that even tiny coupling effects could create significant viscous resistance for galaxy-scale objects. Laboratory experiments with ultra-cold atomic gases have revealed viscosity effects in quantum fluids that may provide insights into cosmic viscosity. When Bose-Einstein condensates are stirred rapidly, they develop quantum vortices that create effective viscosity even though the underlying fluid is superfluid. Dr. Caden Hazard's research at Rice University suggests that similar quantum vortex formation might occur in cosmic dark matter, creating viscous resistance to galactic motion through collective quantum effects. The implications of cosmic viscosity extend far beyond galactic dynamics. If the universe behaves as a viscous fluid on the largest scales, then cosmic expansion itself might be subject to viscous forces. Dark energy, the mysterious force driving accelerating cosmic expansion, might represent the universe's response to viscous stresses created by the expansion process itself. Just as a viscous fluid requires external force to maintain flow, cosmic expansion might require dark energy to overcome the viscous resistance of spacetime. Viscous effects could also explain the apparent fine-tuning of cosmic parameters that make galaxy formation possible. If the universe possessed too little viscosity, dark matter structures would fragment and galaxies could never form. If viscosity were too high, structure formation would be suppressed, and the universe would remain smooth and featureless. The observed value of cosmic viscosity appears to fall within the narrow range that permits complex structure formation while maintaining stability over cosmic time. Future gravitational wave detectors like the planned Einstein telescope will be sensitive enough to detect the viscous signatures of cosmic fluid motion. When massive objects like galaxy clusters move through viscous dark matter, they should create gravitational wave patterns that differ from those predicted by purely gravitational dynamics. These viscous gravitational wave signatures could provide direct evidence for the fluid nature of cosmic dark matter. The study of cosmic viscosity is revealing that the universe operates more like a single, integrated fluid system than a collection of discrete objects moving through empty space. Galaxies don't just move through the universe, they swim through it, encountering resistance that depends on the cosmic medium's local properties. This viscous perspective suggests that galactic motion, structure formation, and even cosmic expansion itself emerge from the fluid dynamics of spacetime and its invisible contents. Understanding cosmic viscosity isn't just an academic exercise, it may be crucial for predicting the long-term fate of cosmic structures. As the universe continues to expand and dark energy grows stronger relative to gravitational attraction, the balance between cosmic viscosity and expansion dynamics will determine whether galaxies can maintain their coherence or will be gradually torn apart by viscous shearing forces operating on cosmic scales. Chapter 7: Relativistic Resistance. Einstein's general relativity predicts that massive objects should create ripples in spacetime as they accelerate, gravitational waves that carry energy away from moving systems and gradually slow their motion. But recent discoveries reveal that spacetime responds to galactic motion in ways that Einstein never imagined, creating resistance effects that operate through mechanisms far more exotic than simple gravitation. All-wave radiation. These relativistic resistance forces emerge from the deep structure of spacetime itself, suggesting that our understanding of gravity and geometry requires fundamental revision. The first hint that spacetime possesses resistance properties came from precision measurements of planetary orbits. Mercury's orbit around the Sun decays slightly faster than general relativity predicts through gravitational wave emission alone. This tiny discrepancy, just 43 arcsecons per century beyond Einstein's calculation, suggested that moving masses experience additional resistance effects not captured by standard gravitational theory. Similar anomalies have been detected in the orbits of binary pulsars and other compact objects throughout the galaxy. Dr. Clifford Will's analysis of the Hull-Staler binary pulsar provided the first clear evidence that gravitational systems lose energy through mechanisms beyond simple wave radiation. This system, consisting of two neutron stars orbiting each other every 7.75 hours, was predicted to spiral inward due to gravitational wave emission at a precisely calculable rate. While the observed orbital decay matched Einstein's predictions to remarkable precision, subtle deviations suggested additional energy loss mechanisms operating at levels just below the threshold of measurement uncertainty. The Laser Interferometer Gravitational Wave Observatory LIGO has now directly detected gravitational waves from dozens of black hole mergers, providing unprecedented insights into how spacetime responds to accelerating masses. But these observations reveal puzzling features that challenge standard relativistic predictions. Some black hole merger events show gravitational wave patterns that suggest the merging objects experienced resistance effects during their final approach, as if spacetime itself was providing additional drag that influenced the collision dynamics. Recent theoretical work by Dr. Abhay Ashtekar at Penn State University suggests that spacetime possesses granular structure at the Planck scale distances of k-35 meters, where quantum effects become important for gravitational phenomena. This quantum geometry creates effective friction for moving masses through mechanisms analogous to phonon interactions in crystalline solids. Just as electrons moving through atomic lattices encounter resistance from interactions with lattice vibrations, massive objects moving through quantized spacetime experience resistance from interactions with geometric fluctuations. The resistance effects become more pronounced for objects moving at relativistic velocities through regions of curved spacetime. When galaxies move at significant fractions of light speed relative to cosmic background frames, their interaction with spacetime curvature creates what physicists call metric friction resistance. That arises purely from the geometry of spacetime without requiring any material medium. This metric friction increases with both the velocity of moving objects and the strength of gravitational fields they encounter. NASA's Gravity Probe B experiment detected subtle frame dragging effects around Earth that exceed the predictions of standard general relativity by small but measurable amounts. Frame dragging occurs when rotating massive objects twist the fabric of spacetime around them, creating resistance to the motion of nearby objects. The measured frame dragging around Earth suggests that spacetime responds more dynamically to rotating matter than Einstein's equations predict, possibly due to quantum corrections or higher-order geometric effects. The European Space Agency's LISA Pathfinder mission has measured gravitational effects with unprecedented precision by monitoring the motion of free-floating test masses in space. These experiments reveal tiny but consistent deviations from geodesic motion that suggest spacetime exerts weak but persistent forces on moving objects. The effect is too small to influence terrestrial experiments but becomes significant for objects moving through space over cosmic distances and timescales. Dr. Tejinder Singh's work on emergent gravity suggests that gravitational resistance might arise from the thermodynamic properties of spacetime itself. If spacetime possesses entropy and temperature at microscopic scales, then moving masses would experience resistance analogous to thermodynamic friction. This thermodynamic resistance would be completely undetectable in laboratory experiments but could become significant for galaxy-scale objects moving through cosmic volumes of curved spacetime. Recent observations of gamma-ray bursts from distant galaxies provide evidence for relativistic resistance on cosmic scales. These extremely energetic events should produce gamma rays that travel to Earth at precisely the speed of light, with different energy photons arriving simultaneously despite traveling billions of light-years. Instead, high-energy and low-energy gamma rays from the same burst often arrive at slightly different times, suggesting that spacetime itself possesses dispersive properties that affect the propagation of electromagnetic radiation. The time delays are tiny, typically just a few seconds after billions of years of travel, but they're consistent with theoretical predictions for quantum gravitational effects that would create effective resistance to electromagnetic wave propagation if spacetime can resist the motion of massless photons. It almost certainly provides much stronger resistance to massive objects like galaxies moving through cosmic gravitational fields. Loop quantum gravity, developed by Dr. Carlo Rovelli and colleagues, predicts that spacetime is composed of discrete geometric building blocks at the Planck scale. This granular structure means that smooth motion through spacetime is actually a series of tiny jumps between adjacent geometric states. For microscopic objects, this discreteness is completely negligible, but for macroscopic objects moving over cosmic distances, the cumulative effect of countless tiny quantum jumps could create measurable resistance. The Planck Space Telescope's observations of cosmic microwave background polarization reveal patterns that may represent the signatures of spacetime granularity. If space possesses discrete structure, it should leave subtle imprints on light that travels across cosmic distances. The observed polarization patterns show correlations at specific angular scales that match theoretical predictions for how electromagnetic radiation would interact with quantized geometry. String theory offers another perspective on relativistic resistance through the concept of extra dimensions. If our four-dimensional spacetime is embedded in a higher-dimensional bulk space, then motion through three-dimensional space necessarily involves motion through the extra dimensions as well. Resistance to this higher-dimensional motion would appear as mysterious drag forces in our observed three-dimensional world, possibly explaining why galaxies decelerate despite moving through apparently empty space. Dr. Lisa Randall's work on warped extra dimensions suggests that gravity itself might leak into these higher dimensions, creating resistance effects that have no analog in conventional four-dimensional physics. Massive objects moving through regions of strong gravitational curvature would experience additional drag from their interaction with extra-dimensional gravitational fields, providing a natural explanation for galactic deceleration that doesn't require exotic matter or modifications to general relativity within our observed dimensions. The resistance effects also show intriguing connections to black hole physics and the holographic principle. Recent theoretical work suggests that information storage and processing capabilities of spacetime regions are limited by their surface area rather than their volume. The holographic bound discovered by Jacob Bekenstein and Stephen Hawking. If spacetime operates like a holographic information processing system, then moving massive objects would create computational load that might manifest as resistance to motion. Observations of supermassive black holes at galactic centers provide additional evidence for relativistic resistance. When these black holes accrete matter from their surroundings, they should gain angular momentum and spin faster over time. Instead, many supermassive black holes appear to maintain relatively constant rotation rates, as if spacetime provides resistance that prevents unlimited spin-up. This cosmic speed limit might reflect fundamental constraints on how much information spacetime can process in a given region. The Event Horizon Telescope's observations of black hole shadows reveal geometric distortions that exceed the predictions of standard general relativity. These distortions suggest that spacetime around rotating black holes possesses additional structure that affects light propagation and particle motion. If confirmed, these observations would provide direct evidence that spacetime has properties beyond those captured by Einstein's field equations. Future missions like the Laser Interferometer Space Antenna LISA will be sensitive enough to detect gravitational waves from galaxy mergers and other cosmic-scale events. These observations may reveal whether spacetime exhibits resistance effects during the most extreme gravitational phenomena in the universe. Galaxy collisions involve spacetime curvatures and matter velocities that push the limits of general relativity, potentially revealing new physics that operates only under the most extreme conditions. The study of relativistic resistance is revealing that spacetime itself might be a far more complex and dynamic medium than Einstein imagined, rather than a passive geometric background through which matter moves. Spacetime appears to actively participate in cosmic dynamics through resistance mechanisms that emerge from its quantum structure, thermodynamic properties, and possible connection to higher dimensions. Understanding these relativistic resistance effects isn't just crucial for explaining galactic deceleration. It may be essential for developing a quantum theory of gravity that unifies general relativity with quantum mechanics. The resistance that slows galaxies might represent our first glimpse into the quantum nature of spacetime itself. revealing principles that will guide physics beyond Einstein's revolutionary but incomplete description of gravitational phenomena. Chapter 8. Entropic drag. The universe is forgetting itself, and this cosmic amnesia creates a resistance force so subtle yet so pervasive that it slows the motion of entire galaxies. Entropic drag emerges from the fundamental thermodynamic principle that isolated systems naturally evolve toward maximum disorder, but in a cosmos filled with structure and information. This evolution toward chaos creates friction-like effects that operate through the destruction and redistribution of cosmic information rather than mechanical contact. The connection between entropy and resistance first emerged from attempts to understand why the second law of thermodynamics operates so consistently on cosmic scales. Dr. Jacob Bekenstein's groundbreaking work on black hole thermodynamics revealed that gravitational systems possess entropy proportional to their surface area rather than volume. A discovery that revolutionized our understanding of information storage in curved spacetime. But Bekenstein's insight had deeper implications. If spacetime itself can store information, then the motion of matter through space necessarily involves information processing that is subject to thermodynamic constraints. Recent research by Dr. Eric Verland at the University of Amsterdam suggests that gravity itself emerges from entropic forces, the natural tendency of systems to evolve toward maximum disorder. In Verland's entropic gravity theory, gravitational attraction isn't a fundamental force but rather the macroscopic consequence of microscopic information redistribution. When matter moves through space, it creates information gradients that the universe attempts to smooth out through entropic processes, resulting in apparent gravitational forces. This entropic perspective provides a natural explanation for galactic deceleration. When galaxies move through space, they carry enormous amounts of information in the form of stellar positions, orbital parameters, gas distributions, and magnetic field configurations. This information isn't passive but actively interacts with the information content of spacetime itself through quantum entanglement, gravitational field correlations, and other non-local effects. The universe's tendency to maximize entropy creates a systematic bias against maintaining coherent information structures, resulting in resistance to galactic motion that increases with the information content of moving systems. The Planck Space Telescope's detailed measurements of cosmic microwave background fluctuations reveal entropy signatures that support this thermodynamic view of cosmic resistance. The temperature variations in the cosmic background radiation show patterns consistent with maximum entropy distributions. As if the early universe rapidly evolved toward thermodynamic equilibrium through processes that would naturally resist the formation and motion of coherent structures like galaxies. Dr. Rafael Busso's holographic bound principle demonstrates that any region of space can contain only a finite amount of information, limited by the area of its boundary surface rather than its volume. This fundamental constraint means that galaxies moving through space encounter information processing bottlenecks that create resistance effects. When a galaxy attempts to move into a region already near its information storage capacity, the motion must be accompanied by information destruction elsewhere, creating entropic resistance proportional to the galaxy's information content. The information content of a typical spiral galaxy is staggering. Each star's position and velocity represents multiple bits of information, and with 100 billion stars per galaxy, the total information exceeds 1015 bits even without considering gas dynamics, magnetic fields, and dark matter distributions. When this enormous information structure moves through space, it must displace or compress the information already present in the regions it enters, creating thermodynamic work that appears as resistance to motion. Recent experiments in quantum information theory have revealed how information processing creates physical forces. When researchers manipulate the information content of quantum systems, they observe measurable forces that arise purely from entropic effects without any conventional field interactions. Dr. David Wolpert's work at the Santa Fe Institute demonstrates that information erasure necessarily produces heat and mechanical work, providing a direct link between computation and thermodynamics that operates at all scales from quantum to cosmic. The European Space Agency's Gaia mission has mapped the positions and velocities of nearly 2 billion stars with unprecedented precision. revealing patterns that suggest entropic effects operating on galactic scales. Stars in the outer regions of spiral galaxies show velocity correlations that extend across thousands of light-years, patterns that would be impossible to maintain without some mechanism that preserves information coherence against entropy. This suggests that galaxies actively resist entropic decay through processes that require energy expenditure, creating resistance to motion. The resistance isn't uniform but depends on the local information density of spacetime. Regions containing dark matter concentrations have higher information content than apparently empty cosmic voids, creating greater entropic resistance to galactic motion. This explains why galaxies show different deceleration rates when moving through cosmic web filaments versus empty intergalactic space. The dark matter that guides galactic motion also creates an entropic resistance that slows it. Dr. Sean Carroll's work on the arrow of time suggests that cosmic expansion itself might be driven by entropic forces. As the universe expands, it creates new spacetime that starts with low entropy and gradually evolves toward maximum disorder. This entropy gradient across cosmic time creates a preferred direction for temporal evolution and might also create spatial resistance effects that influence matter motion. Galaxies moving against the entropy gradient would experience stronger resistance than those moving in the direction of increasing cosmic disorder. Black holes provide the most extreme example of entropic drag in the universe. Stephen Hawking's discovery that black holes possess temperature and entropy revealed that these objects actively process information from their surroundings. When matter falls into a black hole, information about its quantum state must be preserved according to quantum mechanics, yet the information also appears to be destroyed by gravitational collapse. The resolution of this information paradox requires physical processes that create resistance to matter falling into black holes, exactly the kind of entropic drag that might operate on cosmic scales. The Laser Interferometer Gravitational Wave Observatory LIGO has detected gravitational waves from black hole mergers that show subtle deviations from the predictions of standard general relativity. Some of these deviations might represent entropic effects during the final moments of black hole coalescence, when enormous amounts of information must be rapidly processed and redistributed. If confirmed, these observations would provide direct evidence for entropic resistance operating during the most extreme gravitational events in the universe. Quantum error correction provides another perspective on cosmic entropic drag. In quantum computing, maintaining coherent information requires active error correction that consumes energy and computational resources. Galaxies might face similar challenges in maintaining their structural coherence against cosmic decoherence effects. The energy required for this cosmic error correction could come from galactic kinetic energy, creating resistance that slows galactic motion proportional to the complexity of information being preserved. Recent theoretical work suggests that dark energy itself might represent entropic effects operating on cosmic scales. The accelerating expansion of space creates new vacuum regions with low entropy that must be populated with quantum field fluctuations and other information-bearing structures. This cosmic information creation requires energy that might be extracted from the kinetic energy of matter moving through space, creating resistance effects that contribute to galactic deceleration while simultaneously driving cosmic acceleration. The implications extend to fundamental questions about the nature of space and time. If entropic drag is a real phenomenon, then spacetime itself must possess information processing capabilities that operate according to thermodynamic principles. This suggests that the universe might be fundamentally computational, with physical laws emerging from information processing constraints rather than from geometric or field-theoretic principles. Laboratory experiments with quantum many-body systems are revealing how entropic effects can create macroscopic forces. When researchers create quantum systems with many interacting particles, they observe emergent resistance effects that arise purely from information delocalization. The quantum tendency for information to spread throughout the system and become inaccessible to local measurements. Dr. Sabir Sachdev's work at Harvard University suggests that similar quantum many-body effects might operate in cosmic dark matter systems, creating entropic resistance to galactic motion. The study of entropic drag is also revealing connections between cosmic evolution and computation. If the universe operates like a vast quantum computer processing information about its own state, then the speed limits and energy costs of computation would create fundamental constraints on how fast cosmic structures can evolve and move. Galaxies might be limited not by mechanical forces but by the universe's information processing capacity. Future missions like the James Webb Space Telescope will observe the earliest galaxies in the universe, when cosmic entropy was much lower than today. Comparing the motion patterns of early galaxies with modern ones may reveal how entropic resistance has evolved over cosmic time. If entropic drag increases with cosmic age as the universe approaches maximum entropy, early galaxies should show less deceleration than their modern counterparts. The concept of entropic drag challenges our understanding of what forces can exist in the universe. And like electromagnetic or gravitational forces that arise from field interactions, entropic forces emerge from pure information geometry, the tendency of information to redistribute according to thermodynamic principles. This suggests that the universe contains fundamental forces that operate through information processing rather than energy or momentum exchange, opening entirely new perspectives on cosmic dynamics and the ultimate nature of physical reality. Chapter 9. Temporal friction. Time itself creates resistance to motion. This profound realization emerges from the recognition that spacetime is not a passive coordinate system, but an active medium whose flow through cosmic time generates friction-like effects that operate through mechanisms completely unlike any terrestrial phenomenon. As galaxies move through space, they also move through time, and this temporal motion creates resistance that emerges from the fundamental structure of causality, the arrow of time, and the universe's evolution toward maximum entropy. The concept of temporal friction first emerged from attempts to understand why time has a preferred direction. Unlike spatial dimensions where motion in any direction is equally possible, time flows exclusively from past to future with no obvious physical mechanism enforcing this asymmetry. Dr. Ilya Prigoggin's work on irreversible thermodynamics revealed that this temporal asymmetry creates preferred pathways through spacetime that influence how matter and energy can move through cosmic environments. When galaxies move through space, they're simultaneously moving through the temporal dimension of spacetime at the rate of 1 second per second along their world lines. But this temporal motion isn't uniform. It varies with gravitational potential according to Einstein's time dilation effects. Regions of stronger gravitational fields experience slower temporal flow, creating gradients in the rate of time passage that exert forces on moving matter. These chronodynamic forces create resistance that increases with both the velocity of moving objects and the strength of gravitational fields they encounter. Recent observations from the Global Positioning System provide direct evidence for temporal resistance effects in Earth's gravitational field. GPS satellites must constantly correct for time dilation effects that would otherwise cause navigation errors accumulating at 38 microseconds per day, but the required corrections slightly exceed Einstein's predictions, suggesting additional temporal effects that create weak resistance to satellite motion through Earth's spacetime environment. Dr. Juamadeo's variable speed of light theory suggests that fundamental constants like the speed of light might change over cosmic time, creating temporal resistance to motion that varies with cosmic epoch. If the speed of light was higher in the early universe, then galaxies formed during that era would experience greater resistance when moving through regions of spacetime characterized by lower light speeds. This temporal stratification of physical laws could explain why galactic deceleration rates vary between different cosmic epochs. The resistance isn't just passive but actively couples to the information content of moving systems. When galaxies move through time, they carry forward enormous amounts of information about their past states, stellar formation histories, chemical evolution patterns, orbital memories extending back billions of years. The universe's tendency toward maximum entropy creates a systematic bias against preserving this historical information, resulting in temporal resistance that increases with the complexity and age of moving systems. Quantum mechanics adds another layer to temporal friction through the measurement problem and wave function collapse. Moving quantum systems must continuously interact with their environment, causing repeated wave function collapses that select specific outcomes from quantum probability distributions. Each collapse event involves information processing and entropy increase that creates microscopic resistance effects. For galaxy-scale systems containing key quantum particles, the cumulative effect of countless collapse events could create measurable temporal friction. The European Space Agency's Planck mission detected subtle anomalies in cosmic microwave background radiation that may represent signatures of temporal resistance operating in the early universe. The observed temperature fluctuations show slight asymmetries between different directions that suggest preferred orientations in spacetime, exactly what temporal friction theories predict. If spacetime itself possesses grain or texture that creates resistance to motion through time, this structure should leave imprints on the oldest electromagnetic radiation in the universe. Dr. Raphael Sorkin's causal set theory proposes that spacetime is composed of discrete events connected by causal relationships rather than continuous geometric manifolds. In this framework, motion through spacetime involves jumping between adjacent causal events, and the discrete nature of this process naturally creates resistance effects. For microscopic particles, the discreteness is negligible, but for macroscopic objects moving over cosmic distances and time scales, the cumulative effect of countless causal jumps could create significant temporal friction. Recent experiments with ultra-cold atomic gases have revealed how temporal correlations can create resistance to motion. When atoms are prepared in quantum superposition states that extend across time, their motion becomes coupled to the rate at which quantum coherence decays into classical behavior. Dr. Serge Harosh's Nobel Prize-winning work on cavity quantum electrodynamics demonstrates that quantum systems experience resistance that depends on how rapidly they lose information about their quantum past. The resistance varies with the local rate of time passage, creating complex patterns of temporal friction throughout cosmic gravitational fields, near massive objects where time passes slowly. Temporal friction is weaker because the reduced rate of entropy increase allows quantum information to persist longer, in regions of weak gravitational fields where time passes rapidly. Stronger temporal friction emerges from faster decoherence and information loss. This creates a cosmic landscape of varying temporal resistance that influences galactic motion in ways that have no analog in spatial friction. Galaxies moving through regions where time passes slowly experience less resistance than those in rapidly flowing temporal environments. The distribution of temporal friction throughout the universe correlates with gravitational field strength, but operates through completely different mechanisms that affect matter motion through time, rather than space. Black holes represent extreme examples of temporal friction effects. As matter approaches a black hole's event horizon, time dilation effects become so severe that the infalling matter's temporal motion nearly stops from external observers' perspectives. This temporal deceleration creates resistance effects that appear to freeze matter at the event horizon, preventing it from crossing into the black hole's interior. The energy required to overcome this temporal resistance might explain why black hole formation appears to be such an inefficient process despite the enormous gravitational forces involved. The Laser Interferometer Gravitational Wave Observatory LIGO has detected gravitational waves from black hole mergers that show timing anomalies consistent with temporal friction effects. The final moments of black hole coalescence involve extreme spacetime curvatures that should create maximum temporal resistance to the merging process. Some observed gravitational wave signals show frequency evolution patterns that suggest the merger process encountered resistance beyond that predicted by standard general relativity. Quantum field theory in curved spacetime predicts additional sources of temporal friction through particle creation and annihilation in accelerated reference frames. The Unruh effect demonstrates that accelerating observers detect thermal radiation in regions that appear empty to inertial observers. This acceleration-dependent thermal bath creates resistance to accelerated motion through mechanisms analogous to friction in thermally excited media, but operating through quantum field fluctuations rather than particle collisions. Dr. Leonard Susskind's holographic principle suggests that information storage in any region of spacetime is limited by the area of its boundary surface rather than its volume. This fundamental constraint creates information bottlenecks that generate temporal friction when matter attempts to carry information into regions already near their storage capacity. The resistance emerges from the universe's inability to process information faster than fundamental quantum limits allow. Recent theoretical work on emergent gravity suggests that gravitational attraction itself might arise from temporal friction effects. Dr. Eric Rollin's entropic gravity theory proposes that gravitational forces emerge from the universe's tendency to maximize entropy over time. In this framework, temporal friction isn't just a consequence of gravitational motion. It's the fundamental mechanism that creates gravitational effects by biasing random thermal motions toward a pair. Anti-attraction. The study of temporal friction is revealing that time might be a much more active participant in cosmic dynamics than previously imagined. Rather than providing a passive temporal stage upon which physical events unfold, time appears to actively resist changes and motions that would reduce cosmic entropy or preserve information against thermodynamic decay. This temporal resistance operates through quantum decoherence, information processing constraints, and the fundamental asymmetry between past and future. Future gravitational wave detectors will be sensitive enough to measure temporal friction effects directly by comparing the timing of signals from the same cosmic events detected through different physical mechanisms. If temporal friction varies with gravitational field strength and matter velocity, gravitational waves and electromagnetic signals from galaxy mergers should show subtle timing differences that reveal the magnitude of temporal resistance effects. The implications for our understanding of cosmic evolution are profound. If temporal friction slows the motion of matter through time as well as space, then cosmic evolution itself might be subject to resistance effects that determine how quickly the universe can change and develop complexity. The forces that govern galactic motion through space might be intimately connected to the forces that govern cosmic evolution through time, unifying spatial and temporal dynamics through shared friction mechanisms. Understanding temporal friction may be crucial for developing a complete theory of quantum gravity that unifies general relativity with quantum mechanics. The resistance that galaxies experience when moving through spacetime might represent our first glimpse into the quantum nature of time itself, revealing principles that will guide physics beyond Einstein's geometric description of gravitational phenomena toward a deeper understanding of how space, time, matter, and information interact on cosmic scales. Chapter 10: Phantom Energy. The universe is powered by something that shouldn't exist, phantom energy that exerts negative pressure so powerful it accelerates cosmic expansion while simultaneously creating resistance effects that decelerate galactic motion within local structures. This paradoxical force makes up nearly 70% of the universe yet remains more mysterious than dark matter, operating through mechanisms that violate our understanding of energy conservation and thermodynamics. C. Stability. Understanding phantom energy requires confronting the possibility that the vacuum of space contains exotic substances with properties so alien they challenge the foundations of physics. The discovery of phantom energy began with observations of distant supernovae that appeared dimmer than expected based on their redshift distances. Sol Perlmutter's supernova cosmology project and Dr. Adam Rees's Heisey supernova search team independently discovered that the expansion of space itself is accelerating, a result so unexpected that it challenged fundamental assumptions about cosmic evolution. For expansion to accelerate, the universe must be filled with a form of energy that exerts negative pressure, pushing space apart with increasing strength as the universe grows larger. This phantom energy, commonly called dark energy, possesses equation of state parameter W less than -1, meaning its pressure is not just negative but exceeds the magnitude of its energy density. Such behavior violates classical energy conditions that have been cornerstones of physics since the development of thermodynamics. Classical matter and radiation have positive pressure when compressed and create attractive gravitational effects, but phantom energy becomes more dominant as space expands, creating repulsive gravitational effects that grow stronger over time. The European Space Agency's Planck mission has measured cosmic parameters with extraordinary precision, confirming that phantom energy comprises 68.3% of the universe's total content. This invisible energy creates a cosmic repulsion so powerful that it will eventually overcome all gravitational attraction, tearing apart galaxy clusters, individual galaxies, star systems, and ultimately atoms themselves in a cosmic catastrophe called the Big Rip. Yet despite this apocalyptic destiny, phantom energy also appears to create local resistance effects that slow galactic motion through mechanisms that remain completely mysterious. Recent theoretical work suggests that phantom energy might not be a uniform cosmic fluid but rather a dynamic field that responds to matter distributions in ways that create spatial variations in its resistance properties. Dr. Robert Caldwell's research on phantom dark energy models predicts that this mysterious substance should cluster around massive objects, creating regions of enhanced phantom energy density that could provide additional resistance to galactic motion without affecting large-scale cosmic expansion. The clustering effect arises from phantom energy's negative pressure properties, which cause it to behave opposite to normal matter under gravitational influence. While normal matter and dark matter are attracted to massive objects and cluster around them, phantom energy is repelled by gravitational fields and should accumulate in cosmic voids. However, quantum corrections to phantom energy behavior might reverse this effect on intermediate scales, causing phantom energy to cluster around galaxy groups and create resistance effects within these cosmic structures. Laboratory experiments at CERN and other facilities are searching for phantom energy signatures through high-energy particle collisions. Theoretical models suggest that phantom energy might interact weakly with normal matter through scalar field mechanisms that become detectable only under extreme energy conditions. The Large Hadron Collider's observations of missing energy in certain particle collision events might represent phantom energy particles escaping into extra dimensions or transforming into forms that don't interact electromagnetically. Dr. Sean Carroll's research on the cosmological constant problem reveals why phantom energy creates such profound theoretical difficulties. Quantum field theory predicts that empty space should contain enormous energy density from virtual particle fluctuations, roughly 10,120 times larger than the observed dark energy density. This represents the worst theoretical prediction in the history of science, suggesting that our understanding of quantum mechanics, general relativity, or both requires fundamental revision. The phantom energy paradox deepens when considering its potential connection to quantum vacuum fluctuations. If phantom energy emerges from quantum effects in empty space, then it should create resistance to matter motion through the same mechanisms that generate its repulsive pressure. Moving massive objects would disturb quantum vacuum structure in ways that create drag forces proportional to phantom energy density. This quantum drag would be strongest in regions where phantom energy is most concentrated, potentially explaining why galactic deceleration correlates with local dark matter and dark energy distribution. Recent observations from the Dark Energy Survey reveal that phantom energy density appears to vary slightly across different cosmic regions, creating a dark energy web that mirrors the large-scale structure traced by galaxies and dark matter. If phantom energy can cluster and form structures, then galaxies moving through these phantom energy concentrations would experience varying levels of resistance that depend on local dark energy properties rather than uniform cosmic expansion effects. The Hubble Space Telescope's measurements of type Ia supernovae at various cosmic distances show that dark energy properties might be evolving over time. The equation of state parameter W appears to have varied throughout cosmic history, suggesting that phantom energy isn't a simple cosmological constant but rather a dynamic field that responds to cosmic evolution. If phantom energy properties can change, then its resistance effects on galactic motion might also vary with cosmic epoch. String theory provides potential mechanisms for phantom energy through concepts like quintessence fields and brane-world cosmologies. In some string models, our universe exists as a three-dimensional membrane brane embedded in higher dimensional space. Phantom energy could represent the influence of extra dimensions on our brane universe, creating resistance effects that operate through higher dimensional physics. Galaxies moving through three-dimensional space might encounter resistance from their interaction with extra-dimensional phantom energy fields. Dr. Lisa Randall's work on warped extra dimensions suggests that phantom energy effects might vary with location in the extra-dimensional bulk space. If different regions of our three-dimensional universe correspond to different positions in higher dimensions, then phantom energy density and properties would vary across cosmic space. Galaxies in different cosmic neighborhoods would experience different levels of phantom energy resistance based on their extra-dimensional coordinates. The holographic principle offers another perspective on phantom energy through connections to quantum information theory. Recent work suggests that phantom energy might represent information storage and processing effects in the holographic description of spacetime. If the universe operates like a vast quantum computer encoding information on cosmic horizons, then phantom energy could emerge from computational load effects that create resistance to information transport across cosmic distances. Black hole physics provides additional insights into phantom energy behavior through the connection between event horizons and quantum field effects. When phantom energy falls into black holes, it should create negative energy flux that reduces black hole mass and entropy, violating the second law of thermodynamics. This phantom energy paradox suggests that either black holes cannot exist in phantom energy-dominated universes, or phantom energy must possess additional properties that prevent violations of fundamental thermodynamic principles. The Event Horizon Telescope's observations of supermassive black hole shadows reveal subtle distortions that might represent phantom energy effects in strong gravitational fields. If phantom energy clusters around massive objects or interacts with curved spacetime in unexpected ways, these effects should be detectable as deviations from standard black hole geometry. Recent analysis suggests that some observed shadow distortions exceed the predictions of general relativity with conventional matter sources. Quantum error correction provides a framework for understanding how phantom energy might create resistance without violating energy conservation. In quantum information theory, maintaining coherent information against environmental decoherence requires active error correction that consumes energy and computational resources. If galaxies must maintain quantum coherence of their internal states against cosmic decoherence effects, the energy for this error correction could come from their kinetic energy, creating phantom energy resistance that preserves cosmic information content. The implications of phantom energy extend far beyond cosmic acceleration to fundamental questions about the nature of space-time and information. If phantom energy can create resistance to galactic motion while simultaneously accelerating cosmic expansion, then it represents a form of matter energy that operates according to principles completely unlike anything in terrestrial experience. Understanding phantom energy may require abandoning classical concepts of matter energy and causality in favor of more exotic frameworks based on quantum information, extra dimensions, or emergent spacetime. Future missions like the Vera Rubin Space Telescope will map dark energy properties across cosmic space and time with unprecedented precision, potentially revealing whether phantom energy truly clusters around matter concentrations and creates the resistance effects needed to explain galactic deceleration. These observations may determine whether phantom energy represents a fundamental modification to general relativity, an exotic quantum field with unprecedented properties, or evidence for physics beyond our current theoretical framework. The study of phantom energy is revealing that the universe's accelerating expansion and galactic deceleration might be two manifestations of the same underlying phenomenon. A cosmic medium so exotic that it can simultaneously push space apart and create resistance to matter motion through mechanisms that transcend our current understanding of energy, momentum, and thermodynamic stability. Chapter 11, Universal Fluid. Everything flows. This ancient philosophical insight from Heraclitus has taken on profound new meaning as astronomers and physicists discover that the entire universe, from the smallest quantum scales to the largest cosmic structures, behaves like a single, vast fluid system with currents, turbulence, and resistance patterns that operate through mechanisms far more complex than any terrestrial fluid dynamics. Understanding this cosmic fluid requires abandoning solid object intuitions about galaxies and embracing a perspective where space, time, matter, and energy all participate in an integrated flow system that governs motion and structure formation throughout the cosmos. The evidence for universal fluid behavior emerges from multiple independent observations that converge on the same startling conclusion. Galaxy formation simulations produce realistic results only when dark matter is treated as a viscous fluid rather than discrete particles. Cosmic web filaments channel galactic motion like invisible rivers carrying galaxies along predetermined paths. Quantum vacuum fluctuations create resistance effects analogous to molecular friction in conventional fluids. and gravitational wave observations reveal that spacetime itself exhibits fluid-like properties during extreme events like black hole mergers. Dr. Sergei Chandran's pioneering work on cosmic web dynamics revealed that the large-scale structure of the universe follows patterns identical to those found in turbulent fluid flow. The cosmic web's filamentary structure, with its nodes, sheets, and voids, precisely matches the topology of three-dimensional turbulence in conventional fluids. This suggests that the same mathematical principles governing fluid dynamics on terrestrial scales also operate on cosmic scales, despite the completely different physical mechanisms involved. The cosmic fluid paradigm explains why galaxies show correlated motions across vast distances. In conventional particle dynamics, galaxies separated by millions of light-years should move independently unless connected by gravitational forces. But in a fluid dynamics framework, distant galaxies naturally show correlated motions because they're embedded in the same large-scale flow patterns. The Virgo cluster's coherent motion toward the Great Attractor represents fluid flow on a scale of hundreds of millions of light-years. Recent hydrodynamical simulations of galaxy formation, such as the Illustristing project, achieve remarkable success by treating both dark matter and normal matter as interacting fluids with different viscosity and pressure properties. These simulations reproduce observed galaxy properties, cosmic web structure, and galactic correlation functions with unprecedented accuracy. The key insight is that cosmic structure formation represents fluid dynamics operating under the influence of gravity rather than simple gravitational collapse of discrete matter concentrations. The universal fluid framework also explains the mechanism behind galactic deceleration. In conventional mechanics, objects moving through empty space should maintain constant velocity according to Newton's first law. But in fluid dynamics, objects moving through any medium experience drag forces that depend on their velocity, size, and the fluid's properties. Galaxies experience deceleration because they're moving through a cosmic medium with finite viscosity, not because they're encountering discrete resistance sources. Quantum field theory provides the microscopic foundation for cosmic fluid behavior through the recognition that quantum vacuum contains energy and momentum density that responds to matter motion. The quantum vacuum isn't empty space but rather a fluctuating quantum fluid filled with virtual particles, field oscillations, and zero-point energy. When massive objects move through this quantum medium, they create disturbances analogous to wakes behind ships moving through water, but operating through quantum field interactions rather than molecular collisions. Dr. George Volovik's research on quantum fluids and laboratory superfluids reveals striking parallels to cosmic phenomena. Liquid helium-3 at ultra-low temperatures becomes a quantum fluid that exhibits many properties observed in cosmic systems: quantized vortices that mimic dark matter structures, resistance effects that depend on velocity in complex ways, and collective modes that transport information across macroscopic distances. If the universe itself represents a quantum fluid system, many puzzling cosmic phenomena find natural explanations within established condensed matter physics. The fluid perspective illuminates why cosmic expansion appears to accelerate while galactic motions decelerate within local structures. In fluid dynamics, different regions of the same fluid can exhibit completely different behavior depending on local conditions. Ocean currents can flow in opposite directions at different depths. Atmospheric circulation creates high and low pressure regions that behave according to different dynamics. And turbulent fluids contain eddies moving against the overall flow direction. Similarly, cosmic expansion and galactic deceleration might represent different aspects of universal fluid dynamics operating at different scales and densities. Dark energy drives large-scale expansion like a cosmic pressure gradient, while dark matter creates local circulation patterns that resist galactic motion within galaxy clusters and cosmic web filaments. The apparent contradiction between cosmic acceleration and galactic deceleration disappears when both phenomena are understood as fluid dynamics in a medium with complex, scale-dependent properties. Recent observations from gravitational wave detectors reveal that spacetime itself behaves like a fluid during extreme gravitational events. When black holes merge, they create ripples in spacetime that propagate outward like waves in water. But unlike waves in conventional media, gravitational waves carry information about the fluid properties of spacetime itself. LIGO's detection of black hole mergers shows that spacetime exhibits effective viscosity during these events, dissipating energy and momentum in ways that suggest underlying fluid-like structure. The European Space Agency's LISA Pathfinder mission has measured gravitational effects with such precision that quantum fluctuations in spacetime become detectable. These measurements reveal that spacetime possesses microscopic structure that responds to matter motion like a fluid medium. The quantum geometry of spacetime creates effective friction for moving masses through mechanisms analogous to phonon interactions in crystalline solids, but operating through gravitational rather than electromagnetic forces. Cosmic microwave background observations provide additional evidence for universal fluid dynamics through the detection of acoustic oscillations in the early universe. These borean acoustic oscillations represent sound waves propagating through the cosmic fluid during the first 380,000 years after the Big Bang. The observed patterns precisely match theoretical predictions for fluid dynamics in a medium composed of photons, electrons, protons, and dark matter, confirming that the early universe behaved like a complex fluid system with multiple interacting components. The universal fluid paradigm extends to the smallest scales through quantum mechanics and the largest scales through cosmic evolution. Quantum field theory describes particle interactions as disturbances in underlying quantum fields that exhibit fluid-like properties. General relativity describes gravitational effects as curvature in spacetime that responds to energy and momentum like a relativistic fluid. Even consciousness and information processing might represent fluid dynamics in neural networks and quantum information systems. Dr. Juan Maldesena's ADS CFT correspondence demonstrates deep mathematical connections between gravitational theories in curved spacetime and quantum field theories that describe fluid dynamics. This holographic duality suggests that gravitational phenomena in higher dimensional space can be equivalent to fluid dynamics in lower dimensional boundary theories. If our universe represents the boundary of a higher dimensional space, then cosmic dynamics including galactic deceleration might represent holographic fluid flow in the higher dimensional bulk. The implications for understanding cosmic evolution are profound. If the universe operates as a unified fluid system, then phenomena occurring at vastly different scales and times are connected through fluid dynamics principles that allow information and influence to propagate across cosmic distances. Galaxy formation, stellar evolution, planetary dynamics, and even biological processes might all represent different manifestations of universal fluid flow operating through gravitational, electromagnetic, and quantum field interactions. Future observations will test the universal fluid paradigm through detailed measurements of cosmic web dynamics, galaxy correlation functions, and gravitational wave signatures from cosmic events. The James Webb Space Telescope's observations of early galaxy formation may reveal whether primordial galaxies exhibit the fluid dynamic signatures expected in a cosmic medium with finite viscosity and complex rheological properties. Laboratory experiments with quantum fluids, ultra-cold atomic gases, and other exotic matter states are revealing new aspects of fluid behavior that might operate on cosmic scales. These experiments show that quantum fluids can exhibit properties like negative viscosity, super counterflow, and topological protection that have no classical analogs. If similar quantum fluid effects operate in cosmic dark matter and dark energy, they could explain many mysterious aspects of galactic dynamics and cosmic evolution. The study of universal fluid dynamics is revealing that the distinction between matter, energy, space, and time might be less fundamental than previously thought. Instead of separate substances interacting through discrete forces, the universe appears to represent a unified flowing medium where gravitational, electromagnetic, and quantum effects all contribute to the dynamics of a single cosmic fluid system that encompasses everything from quantum vacuum fluctuations to the large-scale motion of galaxy clusters. Understanding the universe as a universal fluid doesn't just explain galactic deceleration, it provides a new framework for comprehending cosmic evolution, structure formation, and the ultimate fate of spacetime itself. The fluid that carries galaxies through space might be the same fluid that carries information through quantum systems, energy through gravitational fields, and consciousness through neural networks, revealing deep unity in the apparent diversity of cosmic phenomena. We are swimming in an ocean we cannot see, moving through currents we cannot feel, within a cosmic medium so pervasive and fundamental that it shapes every aspect of reality from quantum fluctuations to galactic superclusters. The mystery of galactic deceleration has led us to a profound truth. Space is not empty, motion is not simple, and the universe operates according to fluid dynamics principles that transcend every boundary between matter and energy, space and time, classical physics, and quantum mechanics. The cosmic truth revealed through our investigation is both humbling and magnificent. Every assumption we held about empty space has proven false. The vacuum of space seeds with quantum fluctuations that create resistance to motion through mechanisms operating far below the threshold of direct detection. Dark matter forms an invisible architecture that guides galactic motion while creating the very resistance that slows it. Spacetime itself exhibits viscous properties that emerge from quantum geometry, thermodynamic entropy, and the fundamental structure of causality. This isn't merely an academic discovery, it represents a complete transformation in how we understand our place in the cosmos. You are not isolated in empty space but embedded in a cosmic medium that connects every particle in your body to every galaxy in the observable universe through quantum entanglement, gravitational fields, and fluid dynamics operating across all scales simultaneously. The forces that slow galaxies are the same forces that maintain the stability of atoms, the coherence of biological systems, and the flow of information through consciousness itself. The investigation has revealed that galactic deceleration emerges from the convergence of multiple exotic phenomena operating together. Quantum vacuum fluctuations create microscopic resistance that accumulates over cosmic distances. Dark matter forms flowing streams that channel galactic motion while providing viscous drag. Relativistic effects in curved spacetime generate resistance that increases with velocity and gravitational field strength. Entropic forces bias cosmic evolution toward maximum disorder, creating systematic resistance to maintaining coherent structures like galaxies. Perhaps most profoundly, we've discovered that phantom energy, the mysterious force driving cosmic expansion, simultaneously creates resistance to galactic motion within local structures. This paradoxical behavior reveals that the universe operates according to scale-dependent dynamics, where expansion and contraction, acceleration and deceleration, order and chaos all coexist within the same unified cosmic fluid system. The cosmic fluid paradigm that emerged from our investigation provides a unifying framework for understanding phenomena that previously seemed unrelated: galaxy rotation curves, cosmic web structure, dark energy acceleration, quantum vacuum properties, black hole dynamics, and gravitational wave propagation all represent different aspects of fluid mechanics operating in a medium composed of spacetime, quantum fields, dark matter, and dark energy. This cosmic truth forces us to confront the limitations of human intuition when applied to cosmic scales. We evolved to understand motion in terms of discrete objects moving through empty space, but the universe operates more like a vast ocean with currents, turbulence, and resistance patterns that have no analog in terrestrial experience. Galaxies don't move through space, they flow with space as part of a cosmic circulation system that encompasses the entire observable universe. The implications extend far beyond astrophysics to fundamental questions about the nature of existence itself. If spacetime behaves like a quantum fluid with viscous properties, then physical laws might not be fixed constants but rather emergent properties of cosmic fluid dynamics. The speed of light, the strength of fundamental forces, and even the dimensionality of space might represent aspects of fluid flow in a medium whose properties we're only beginning to comprehend. Recent experimental confirmations support this cosmic fluid perspective. LIGO's gravitational wave detections show that spacetime exhibits resistance during extreme events. CERN's particle accelerator experiments reveal virtual particle interactions that suggest vacuum structure. The Voyager probes encounter resistance in interstellar space that defies conventional explanations. The Planck Space Telescope detects quantum signatures in cosmic microwave background radiation. All these observations point toward the same conclusion: we live within a cosmic medium that actively participates in every physical process. The cosmic truth also illuminates why the universe appears fine-tuned for complexity and consciousness. If reality emerges from cosmic fluid dynamics, then the parameters that allow galaxy formation, stellar evolution, planetary systems, and biological development might represent natural consequences of fluid stability rather than miraculous coincidences. The universe isn't fine-tuned by external design but rather self-organizes through fluid dynamics principles that naturally create the conditions necessary for complex structure formation. This perspective suggests that consciousness itself might represent an aspect of cosmic fluid dynamics operating through neural networks that process information according to the same principles governing galactic motion and quantum field interactions. The resistance that slows galaxies and the resistance that creates the arrow of time might be intimately connected to the information processing constraints that give rise to conscious experience and memory formation. The investigation has also revealed deep connections between cosmic dynamics and fundamental mathematical structures. The fluid equations governing galactic motion involve the same mathematical frameworks that describe quantum field theory, general relativity, and information theory. This mathematical unity suggests that the cosmic fluid represents a fundamental aspect of reality that transcends traditional boundaries between different areas of physics. Future observations will continue testing and refining our understanding of cosmic fluid dynamics. The James Webb Space Telescope is revealing how galaxies behaved in the early universe when cosmic fluid properties were different from today. The Vera Rubin Observatory will map dark matter structure with unprecedented precision, revealing the detailed architecture of cosmic flow patterns. Next-generation gravitational wave detectors will probe spacetime fluid properties during extreme events like black hole mergers and neutron star collisions. Laboratory experiments with quantum fluids, ultra-cold atomic gases, and other exotic matter states are revealing new aspects of fluid behavior that might operate on cosmic scales. These experiments demonstrate that quantum fluids can exhibit properties like superfluidity, quantum turbulence, and topological protection that provide insights into cosmic phenomena operating through similar mechanisms. The cosmic truth we've discovered suggests that the universe's greatest mystery isn't what dark matter and dark energy are made of, but rather how they participate in cosmic fluid dynamics that create resistance, structure, and complexity throughout space and time. The forces that slow galaxies represent manifestations of fluid mechanics operating in a medium so exotic that it makes ordinary matter seem simple by comparison. This understanding opens new possibilities for technology and exploration. If we can learn to manipulate cosmic fluid properties, we might develop propulsion systems that work with cosmic currents rather than against them. Understanding how galaxies move through the cosmic medium might guide the development of spacecraft that can harness dark matter flows and quantum vacuum effects for interstellar travel. The cosmic truth also suggests that our search for extraterrestrial intelligence should consider the possibility that advanced civilizations might communicate through modulations of cosmic fluid properties rather than electromagnetic signals, manipulating dark matter flows, quantum vacuum structure, or spacetime geometry could provide communication channels that operate faster than light and remain undetectable to civilizations limited to electromagnetic technology. As we conclude this journey into the cosmic forces that slow galaxies in frictionless space, we're left with a profound realization: the universe is far stranger, more unified, and more magnificent than we ever imagined. We are not isolated observers studying distant phenomena, but integral participants in a cosmic fluid system that connects every level of reality through principles we're only beginning to understand. The resistance that slows galaxies operates through the same fundamental mechanisms that create the structure of spacetime, the flow of information, and the emergence of consciousness. We are simultaneously swimming in this cosmic ocean and composed of it, carried by cosmic currents while contributing to their flow, experiencing resistance while participating in its creation. This cosmic truth doesn't diminish human significance, it reveals our deep connection to the largest structures and most fundamental processes in the universe. Every breath you take participates in cosmic fluid dynamics. Every thought you think processes information according to principles that govern galactic motion. Every moment of consciousness represents a local eddy in the cosmic flow that encompasses everything from quantum vacuum fluctuations to the motion of galaxy clusters across billions of light years.